So we've got a differential equation, dy dt equals y squared. The right-hand side here is just a function of y. We call it f of y. In general, it could be a function of t as well. When you look at this differential equation, though, it is important that you think this way consistently. We're looking for a function, y is a function of t, whose derivative with respect to t is not literally y squared, but it's the function squared. When you replace y with the function of t and square it and simplify, you get the same thing as if you take the derivative. Your initial condition was y of 0 equals 1. I'm going to do an arbitrary initial condition here, y of 0 equals y naught, to illustrate, for one thing, that you can, and for a second thing, that I want you to be able to do so. I didn't have you do it today, but I do want you to be able to do so in general. But before we find the solution with the separation of variables, as you did in part B, let's think about part A, where you try to draw a rough sketch of the slope field and try to draw your solution with initial condition y of 0 equals 1, but I'll think about other initial conditions as well. The slope field is drawn in a ty plane. And the key thing again is, for any point in this plane, say this point right there, you look at its coordinates, its ty coordinates, you plug them into the right-hand side function of the differential equation, which in general could involve a t, but in this case it doesn't, it just involves y. So in fact, that means for this example, t doesn't matter. Only the y coordinate of the point matters. Plug it in there, and you draw a little line segment with the resulting slope. Now, if the y coordinate of that point is, say, 1, that means the slope will be 1 squared, 1. If I go up to a point where y is 2, 2 squared is 4, so you draw a line with a slope of 4. And those lines are just going to get steeper and steeper as you keep going up. Never are they vertical, but once you're high enough, they're going to look vertical, right? Because they're going to be so steep. When y gets close to 0, say a half, y squared, 0.5 squared is 0.25. Your slopes are still positive, but they're getting pretty close to 0. And because the right-hand side is independent of t, these lines that I drew are going to be the same slope if along any horizontal line. If I draw any horizontal line with the same y coordinate, I'm going to get lines that are parallel with the same slope along that horizontal line. So these lines that I'm drawing all have a slope of 1. These lines, say, all have a slope of 0.25. At y equals 2, where 2 squared is 4, and I have slopes of 4, these lines all have a slope of 4. And as I keep going up, the slopes keep getting bigger. But again, along any horizontal line, the slopes are parallel. The slopes are equal, the lines are parallel. What about when y is 0? That's the t-axis. Any point along there has a 0 y coordinate, 0 squared is 0. I get a bunch of horizontal lines along the t-axis. That must be a solution that's constant at y equals 0. It's called an equilibrium solution. When y becomes negative, since I'm squaring it, I get a positive slope still, close to 0 when y is slightly negative, and getting steeper as y becomes more negative. Something like this. Your initial condition was y of 0 equals 1. Let's say that's right here. The solutions are supposed to follow the slope field. The differential equation geometrically is saying solution curves have derivatives, slopes, that everywhere equal their y coordinate as you move along the curve. And the y coordinate changes, so the slope changes. So what that means is the solutions have to be tangent to these little line segments anytime they pass through, say, the midpoint of one of them, if you draw them to be centered at the midpoints. So your solution is going to look something like that as t increases, and something like this as t decreases. Looks like it might be exponential growth for all you can tell. There are other solutions for other initial conditions. If I have a small initial condition close to 0, my solution is going to go out here a ways before heading upwards. If I have a large initial condition, it's going to be going up pretty fast right away. But as t goes backwards to minus infinity, it looks like it still goes towards 0. Solutions whose initial conditions are negative do behave differently. They're still increasing, but whereas when y is positive, it looks like there's a horizontal asymptote as t goes to minus infinity. When y is negative, y naught is negative, it looks like there's a horizontal asymptote as t goes to plus infinity. And yeah, there's this constant function, it seems, y equals 0, that must be a solution as well. Yeah, the constant function at 0 does have a derivative that's always 0, and 0 squared is 0. That's a constant function. Y of t is always 0. Solves the differential equation. It's called an equilibrium solution. When you've got a constant function that solves the differential equation, it's called an equilibrium solution. You might wonder, is it really going to be a horizontal asymptote here for like one of these? Or could it possibly touch the t-axis? We're going to see next week that it can't possibly touch the t-axis. It does have to be a horizontal asymptote that doesn't touch the t-axis. But that's a question you might have in your mind. All right, so that's a decent sketch of the slope field. Let's now solve this generic initial value problem with separation of variables. Divide both sides by y squared and quote unquote multiply both sides by dt. And then integrate. Say t plus c1 on the left. This is integrating y to the negative 2 power. Right? 1 over y squared is y to the negative 2 power. So when you integrate this one, you're going to get negative y to the negative 1 power. Or y to the negative 1 power over negative 1. Put the negative sign more in front of it here. Multiply both sides by negative 1 first. And write y to the negative 1, say, is 1 over y. I'll say C2 is negative C1, and just use another constant. Now, take the reciprocals of both sides to solve for y. And maybe I'll just call it C now instead of C2. C equals C2. So there's a general solution. Though I will say it's not an ideal general solution, because there's no choice of C that's going to give you the equilibrium solution at y equals 0. This function is never going to equal 0. But let's still see if we can solve a generic initial value problem. We might be able to if we make a modification to it. Let's see what happens. Y naught equals y of 0 equals 1 over negative 0 plus c, which is 1 over c. That means c is 1 over y naught, at least if y naught is not 0. Makes sense. We're missing that equilibrium solution at 0. So for your problem, y naught was 1. You should have got c equals 1. And 1 over negative t plus 1, or if you prefer, 1 over 1 minus t as your solution. But I'm going to do something a little different here with this generic initial condition. There's c, 1 over y naught. I'm going to multiply the top and the bottom of this fraction by y naught so that I don't have fractions within fractions. And in doing so, something magical occurs. I also switched around the order on the bottom. Something magical occurs as if by magic, that function is defined when y naught is 0. And it equals 0 when y naught is 0. Isn't that cool? Was that an accident? Was it magic? It feels like magic, but it just does work out nicely. Okay, this, if I go back to my phi notation, is going to be a solution function, and I'm going to emphasize the initial condition is y naught. If y naught is fixed, that's the unique solution of the initial value problem. And yes, when y naught is 1, it's 1 over 1 minus t. Okay, but I do want you to start getting used to this notation. There's the unique solution. By the way, you should certainly be able to check that it says the unique solution. Plug it in the left-hand side of the differential equation, LHS. That means find its derivative. You could use prime notation. Phi sub y naught prime of t. Maybe it's nicer to write this in this way so we can avoid the quotient rule. Bring down that -1. Make it a -2. Use the chain rule, multiply by a factor of the derivative of the inside. That'll be a negative y naught. Simplify this. We could write it as y naught squared, the negative signs cancel, divided by 1 minus y naught t squared. And hey, you can see this right away. That's the same as y naught over 1 minus y naught t quantity squared. In other words, it is the same as the function squared, which is the right-hand side of the differential equation, y squared. So here I did a verification that it solves the differential equation in one line. Typically, I advocate 2 lines. Left-hand side is the derivative, simplify it. Right-hand side is f of t comma y, replace y with the function, simplify, see if you get the same thing when you simplify. But here I did it in one line. Make sure you can do this on tests. Maybe not for this example, but the idea, you should be able to do this to verify a solution. As far as the initial condition, plug in t equals 0 into that formula there. You're going to get y naught over 1 minus y naught times 0. But that is y naught over 1, which is y naught. I plugged it in up there. All right, what about approximating the solution with Euler's method? Let's go ahead and take y naught equal to 1. So now we're using Euler's method, getting a little practice with that. Delta t equal to 0.5. We're doing a particular initial value problem, the one you did. Y of 0 equals 1. In other words, y naught equals 1. And let's do 2 steps and see what happens. And see if there's a problem. Is there a contradiction? So the first thing you do, you can do this with a table. Write down the values of t, 0, 0.5, and 1. Write down the values of y that come from Euler's method. Call them y sub k or y sub n or whatever you want to call them. Guess I should have a column for k, technically speaking here. K is the step number. T sub k is the t value. Y sub k is the approximate y value. At t equals 0, it's 1. We use the initial condition. Then you do f of tk comma yk times delta t. That's the key step of Euler's method. Is to compute that. Where does that come from? I talk about in the lectures. Without going into detail, I'll just say it's related to the slope field and slopes in the slope field. So this is f of 0, 1 times 0.5. Our f function just depends on y, but you could call it f of ty anyway, even though you don't see a t. The t doesn't matter. Only y matters. We got to do 1 squared. So we get 0.5, and that number becomes the approximate change in the solution. So our approximation for how much y changes is 0.5, so it's going to go from 1 to 1.5. Effectively, we're using the tangent line in the slope field at the initial condition, following it forward 1/2 a unit in time and seeing how much y changes. And 1.5 is the second coordinate of the new point on that tangent line. Does it equal the solution curve there? No, it doesn't. It's an approximation. The true solution, again, for this initial value problem, phi sub 1 of t, the initial condition is 1, is 1 over 1 minus t. When you plug in 0.5 into that, you get 1 over 0.5, you get 2. The actual solution has a value of 2 when t is 0.5. This is just an approximation, not a great approximation. If we use the smaller value of delta t, we can get better approximations, though, for example, if we use delta t as 0.1, we'd be getting a better approximation at 0.1 in the first step. And after 5 steps, a better approximation at 0.5. For the next step, we need to plug in these t and y values, but again, only the y value matters. F of 0.5 comma 1.5 times 0.5 will be 1.5 squared times 0.5. 1.5 squared is 2.25. Half of that is 1.125. Did I do that right in my head? That's the approximate change in the solution. So I have to add that now to 1.5 and get 2.625. So there's y2. There's your approximation for the solution at time 1. So time 1 because delta t is 0.5. And what's the contradiction? What's the problem? Compare that with the solution. What's the problem? Go ahead. Yeah, phi or phi of 1 is undefined. It's undefined when t is 1. The graph of this has a vertical asymptote. You wouldn't know that, by the way, just drawing the slope field. I mean, you knew it went up fast, but you wouldn't know necessarily that it's got a vertical asymptote. But it does. It's not exponential growth. It's faster than exponential growth. There is such a thing. This is one example. And in general, actually, this has got a vertical asymptote at where the bottom is 0, which is 1 over y naught. And as y naught gets bigger, that gets smaller. The vertical asymptote, if y naught is large, like in this case, occurs very quickly. This reaches a vertical asymptote very quickly. Doesn't this kind of seem bad? Like, why would you want solutions to have vertical asymptotes? Well, it's not that we want them to have vertical asymptotes, it's just sometimes they do. For a real-life application, what would that mean? Well, maybe it means this equation has no real-life applications, or maybe it could have an application, I don't know, to studying black holes. I'm kind of making things up as I go here. Because at black holes, there are singularities and, you know, where physics breaks down, and the solution going off to infinity is kind of like that, you might say. It's like the force of gravity in a black hole going to infinity as you approach the singularity. Okay, that's just a made-up application. I have no idea if this really applies to black holes. Probably not. It's too simplistic, right? But maybe that's a situation where singularity is going to happen. But just be aware, then many differential equations can have solutions that have vertical asymptotes. And then the bigger important issue for you as far as that goes is that means you should not completely trust the output of Euler's method as far as giving you very accurate answers. Even if I used a smaller value of delta t, like 0.1 instead of 0.5, or even 0.01, if I use 0.01, yes, it'd be pretty accurate at first, but as we approach 1 after 100 steps, we'd still be approaching that singularity and we'd still be getting finite numbers here. They'd probably be big finite numbers, but they'd still be finite. And you would not realize, if you didn't know the true answer, that there's a singularity, a vertical asymptote. Okay. I'm forgetting what lecture I do this in. It's lecture 4 or 5, but I think it would be good to spend at least 5 minutes showing you how to use Mathematica to do the Euler's method here. So again, we're looking at this initial value problem. Yes, in general, the right-hand side is f of ty, and you want to account for that in Mathematica in general, but I could just do f of y in this case. Because it does just depend on y. Here again is how you define a function in Mathematica. Square brackets for function inputs. And when you're first defining it, use an underscore. That is essential. The colon is not essential, but force of habit, I just do it. There are certain situations where it is helpful. I'll just put it that way. It's not really essential. It's just helpful. Out of force of habit, I do that. Oops, not a capital Y. Lowercase y squared. Enter that. That function is now entered. If you are unsure, you can always type f of y without an underscore and see, yes, it is y squared. To do Euler's method efficiently in Mathematica, and by efficiently, I mean in situations where you might need to do 100 steps, you want to use a built-in command called NestList. What NestList does is function iteration, which is really what we're doing with Euler's method. We are iterating an equation, essentially. The equation, I didn't write it down before, is essentially this one. Y sub k or y sub n, I'll go back to an n here. Y sub n, the nth value of y is the preceding value of y plus this change in y, f of t sub n minus 1 comma y sub n minus 1 times delta t. And it's really this function right there that is being iterated, used over and over again. Question? Is this y equals mx plus b? Well, in a sense, that's kind of like the m, that's kind of like the x, and that's kind of like the b. But you could easily misinterpret that. Okay, and this is a slope, but that's not really a y-intercept. Okay, that's the function that I'm going to iterate. I tend to give the function a name, EM in this context, standing for Euler's method. Do I have to? No, but it's just what I do. You want the input to be two-dimensional. And it's definitely convenient to use a list with curly braces. I'm defining this function for the first time, and so I need the underscores. Effectively, this list with a t-coordinate and a y-coordinate, you could think of as being a point. It's a two-dimensional point that's being plugged into this function. Why do I need a two-dimensional point? Because in general, I need to know t and y. If it's going to have a two-dimensional input and be iterated, I need a two-dimensional output as well. Curly braces. T plus whatever delta t is for the first coordinate of the output. Delta t is 0.5. And y plus the f function times delta t for the second coordinate. That effectively, without subscripts, in the second coordinate at least, is applying this formula. In the first coordinate, I just keep updating the value of t by delta t. I keep adding delta t to get the next value. Notice there's no subscripts in the Mathematica. The subscripts are just for your convenience when you write it by hand, to keep track of your step. But as far as Mathematica is concerned, I don't need subscripts. This function then gets entered and then iterated with NestList, and this is the way you do it. And for example, so the function name is EM, standing for Euler method. That's what goes here, is the function name. You don't need the inputs for the function, just the function name. Here's the initial condition, 0, 1, and here's the number of steps. And lo and behold, I get the 2.625 that I got by hand after 2 steps. Again, Mathematica, Euler's method doesn't know there's a vertical asymptote. You could be very, very bad here and continue going on, say 10 steps, and get very bad answers. This is not reflecting what's going on with the solution. Though it is growing, we're still missing that vertical asymptote. I could change delta t to say 0.01, re-enter this, and after 10 steps, that's probably pretty accurate. But after 100 steps, we'd be into inaccuracies, once again missing the vertical asymptote. And yes, it did just do 100 steps just like that there. Okay? So that's a quick intro into how to use Mathematica to implement Euler's method.